we discuss about refraction of light, the model questions for our, okay. Now, most of the cases in this refraction of light, we are having more number of questions, they are asking particularly on the lens and its properties. As we know that we are having two types of lens we have, that is of convex lens and a concave lens. We can say that as a double convex lens or a double concave lens, that is. Most of the cases, the properties of this convex lens and concave lens only many number of questions they are asking, okay. When come to the case of this convex lens, actually convex lens is a converging lens, that is, of which converging the lens means when you project a parallel beam of light rays onto a convex lens, after refraction all the light rays are going to meet at a point. So, that point only we call that as a principal focus, okay. And in the same way, if you come to the case of this concave lens, that is, concave lens is having a nature diverging nature. So that whenever if you focus a parallel beam of light rays onto this concave lens, what happens there is the light rays are going in different directions as they are moving away from each other. So, which means they are going to meet, appears to meet at a point. So, that is why it is having a virtual focus is present, whereas virtual focus means not a real focus, that is, okay. Then based on this converging and diverging nature of these two different lens here, depending on their converging and diverging nature, the image formed by that is also will be different we have. So, based on these image formations, we are having number of questions are there, and these lens follows different properties there when the light rays are passing through that one. We have to make sure that the lens of which we are taking, okay, that refraction takes place about completely about the material you are using, that refractive index we have, okay. Whatever the light you can use, that is not affecting the refraction effect here, okay. For example, like this, if you take a question there, the part of the lens, for example, means here the part of the lens, let us suppose if you are taking a concave lens you can take, or a convex lens you can take. For example, this is a convex lens and here you can take a concave lens. Through these two lenses here, the part of the lens through which the light ray passes undeviated here. So, which means there is no refraction effect, there is no like converging, there is no like diverging here, which means the light ray is passing without any change in its deviation. So, through which part that is possible, that is the question, of which we are having the options, that first one given, that is of focus, and second one given optic center, and third one given the center of curvature, and fourth one given pole, okay. So, focus, optic center, center of curvature and pole, that is. Now, if you see the options, if you are taking the focus here, whenever if the light ray is passing through the focus here, after refraction we know that the light ray will pass as parallel to the principal axis, means there is a change in the path of the light ray takes place. For example, like this, if you take for the case of convex lens, if this is the focus, actually after refraction what happens there is that is passing parallel to the principal axis there like this. So, means there is a refraction effect takes place here. So, the light ray, the actual path has to follow is going like a straight line, but because of due to that lens the light ray is passing parallel to the principal axis here. So, there is a deviation takes place. So, that is why we cannot take this focus here, that is wrong. Whereas, in case of this optic center you took, optic center is nothing but the geometric center of the given lens, that is, you can take a convex lens or you can take a concave lens. This geometric center only we call that as optic center. Then, when the light ray passes through this optic center, what happens there is the light ray passes without any deviation, like a straight line it passes, or even you can take in case of concave lens also. It continues there like passing through without any deviation here, okay. Now, as according to the given question there, the part of the lens through which the light ray passes undeviated, means in this case of when the light ray passes through the optic center here, what happens there is the light ray passes without any change in the path, which means there is no refraction effect takes place when the light ray is passing through the optic center here, okay. So, that is why the correct option is nothing but optic center. Now, if you see one more question there, that is convex lens, which is the converging lens, that is convex lens gives a real image. A real image means which is after refraction the light rays are going to meet really at a point, okay. So, now the question given is the convex lens gives a real image when object is placed at, when object is placed at. Okay. Now here given options are option A given at focus, B beyond focus, and C at C center of curvature, and D between focus and optic center here. Okay. Now convex lens gives a real image when object is placed at focus only, beyond the focus, at C, and between F and O, that is. Now if you see the properties or the ray diagrams of this convex lens, if you are taking convex lens, we are having total 6 positions are there, starting from infinite. Slowly when you are coming closer towards the lens here, there are 6 different positions we have. Those positions are nothing but here optic center, this is a focus, and this is center of curvature. And the first position becomes when object is placed at infinite, that is, and object is placed in between C and F, that is the second position, and third one on the center of curvature, and fourth one between C and F, and fifth one it is on the principal focus. And the sixth position is, which is a special case, that is object is placed in between focus and optic center here. These are the 6 positions we have when object is placed before this convex lens you are taking. Okay. But if you observe the image formed by in all these cases, and the first case when object is at infinite here, as the object is at infinite, the image is formed at the focus, which is a real one, that is, and when object is placed in between infinite and C, here there also we are having a real image is formed there, which is inverted again. And when you are placed that exactly at the center of curvature, even that case also we are having a real and inverted image is formed there. Whereas in between C and F, if you take, there also we are having a real and inverted image is formed. And at the focus, the image is formed at infinite, which is a real and inverted image is formed. And when come to the case of between focus and optic center, if you take, here the convex lens actually gives a virtual image, which is the special case here, which is a magnified image it is forming. So means other than between F and O, remaining all cases we are having a real image is formed here. So which means that the convex lens gives a real image when object is placed at anywhere after the focus. Means here in this case given the first option, which is at focus only. So no need to be at the focus, it may be any position from focus to infinite here. And the second one given beyond focus, that is beyond focus means after the focus we can take any position, that is any place you can take. Whereas in case of C given at the center of curvature only, this also wrong one, and D given between F and O, this also wrong one. So the answer is actually here beyond principal focus, anywhere you can take other than focus. Now one more question, if you see, if the parallel rays of light entering a convex lens, if a parallel beam of light rays, if you take a parallel beam of light rays again, okay. So here given question is parallel beam of light rays enter onto a lens after refraction, it passes through center of curvature, undeviated, passing through principal focus, and parallel beam is given there. Okay. Then which means that if you are taking a convex lens, for example, if you are taking a parallel beam of light rays like this, if you are taking 2 parallel beam of light rays like this, after passing through that, following the rule 1 in the ray diagrams here, any light ray which is going parallel to the principal axis, after refraction the light ray passes through principal focus, that is like this downwards. And whereas if you are taking that another light ray which is again parallel to principal axis, even this also passes through principal focus here like this. Okay. Which means then the parallel beam of light rays after refraction there is a deviation takes place, refraction phenomenon takes place, but it is not passing through center of curvature and it is not undeviated, but that is of passing through principal focus. So passing through C and undeviated and going like again like a parallel beam, these are wrong, and option 3 passing through principal focus only, correct here, following the rule 1 of our ray diagrams, that is. Next, if you see another question, if you want to get a real image, and inverted, okay, see the question there, to get a real image and inverted image and of same size here by using a convex lens where to place the object. Now actually here given options are given, option A given at focus, B given at 2f twice the focal length, and C given at infinite, and D given between f and c, that is. These are the given options at f, at 2f, at infinite, between f and c, that is. Okay. Now given that here mainly three important characteristics are given: real image, inverted image, and of same size is given there. Okay. If you want to get a real and inverted image, convex lens other than between focus and optic center, in all cases it forms the real image there. But depending on the position of the object, we know that it is forming different size of the images here. Whereas in this case, it is forming real and inverted, which means that is not about between f and o. Whereas it is given that the size should be same. Okay. So in case of the same size formation, actually the image we have to take the object exactly on the center of curvature here, or this is center of curvature only, call that as twice the focal length, that is, which is 2f. If object is placed at a center of curvature like this, then after refraction what happens there is the light ray passes through that and the image is formed exactly on the, again on the center of curvature here, like this. Okay. As it is forming exactly on the center of curvature, the object distance and image distances both are same, and the magnification value becomes 1, because magnification m is equal to v by u, that is, of which here the object distance and image distance both are same. That's why here the magnification becomes 1, that is, as the magnification 1, which means that the object is of same size here. As it is forming the inverted image here, we are getting m is equal to -1, that is, which is of inversion takes place. Okay, that minus represent the image formed is a inverted image, that is. So as m is equal to v by u here, and v and u both are equal in this case, because both are formed at the center of curvature, then m is equal to, which is of, for example, u by u you can take, that is of -1 we are getting, because the object distance we have to take here, it is of minus. So that's why you will get there -1, where that minus represent, that is a inverted one, and 1 represents, that is of same size. Okay, and that all inverted images we know those are of real images, that is. So the real image, inverted and same size, when using a convex lens, that is possible only when the object is placed at focus center of curvature, where that center of curvature position is nothing but this b at 2f. Now we will see one more question, that is of the SI unit of power of the lens. SI unit of power of the lens. If you are taking the SI unit of power of the lens, where power of the lens means nothing but the degree of converging or diverging the light rays, that only we call that as power of the lens. Now we are taking its SI unit, and given options are meters, second one centimeters, third one watts, and fourth option given, that is of diopter, that is. Okay, SI unit of power, whereas power it is nothing but how much it is converging or diverging the lens here. So that is equal to 1 by f, where f means the focal length here. Okay, this is nothing but focal length, but this focal length we have to take that in meters. The reciprocal of focal length of the given lens is nothing but called as power, which means the power and the focal length both are inversely proportional to each other. Power and focal length both are inversely proportional to each other. Having more focal length, always the power of the lens is less, and when you are having less focal length is there, then its power is more we have, like that. So that's why both are inversely proportional to each other, that is. Then if you are taking in case of this one 1 by f, that f we have to take that in meters. So the SI unit becomes, which is as it is of 1 by meters is there, that 1 by meters we can also write that as meter inverse. This meter inverse we call that as diopter. That is called as diopter, that is meter inverse. So it's not the meters, it's not the centimeters, it's not the watts. Actually watts it is for electric power we use, not for the case of the power of the lens in light. Okay. Whereas the fourth option, diopter, that is the correct one. Whereas this diopter we can also write that as meter inverse or 1 by meter, that is. Okay. That is the SI unit of power of the lens. If the power of the lens, next question if you see, if the power of the lens is given as 1D, okay, 1D is the power of the lens, then its focal length is, then we need to find the focal length here. And it is given there 1 diopter, that is the power of the lens given there. So we know that the power of the lens, power is equal to 1 by focal length, that is. Okay. As power is equal to 1 by focal length, that focal length we are taking that in meters, that is. Okay. Then power is equal to already given there, which is 1D is given, which is 1 by F. Then F is equal to 1 by 1, that is. This one we are taking in meters, that is. Okay. So then focal length becomes, which is of 1 by F, F is equal to 1 by D, that is. Okay. That D we are taking the data of meters inverse, that is diopter units. Then it becomes 1 meter or it is equal to 100 centimeters, that is. So the focal length of the lens in the given case is, if 1D is the power of the lens, then 100 centimeters is going to be the focal length here. But not only that, if you see, as there is no sign is given, which is nothing but a plus, that is. Whenever if a plus is given for the case of the power, then it represents the image formed is an erect image, which means the image we are getting is just like the object. If the object is above the principal axis, then image is also forming above the principal axis here. Okay. Those type of images only we call that as erect images, which are formed by these our concave lens. That plus 1 represents, that is of a virtual and erect image, that is of which this image it is formed by a convex lens having the focal length which is equal to 100 centimeters, that is. Then if you see this a simple microscope, whenever if you want to see an enlarged and a magnified images, we prefer this microscope here. Okay. Then in case of this microscope, actually we are having two types of lens are there. One is the eye lens, which is at front we are having that, and another one we call that as objective lens, that is. Okay. So that one is just before the object we are taking it at here like this. Okay. So these are the two lenses we are having inside that microscope. One is called the objective lens and another one we call that as eye lens, that is. This is the objective lens and this is our eye lens. Eye lens means towards our eye we are having that lens is present. Okay. So that eye lens and the objective lens, that is. Objective lens means whenever if you are focusing the microscope here, for example like this, if you want to see any of the bacteria or any of the virus here, for example at this position, okay, then we have to take our microscope, should be focused on that one, of which this one which is closer to the object, this we call that as objective lens. And whereas towards which side we are having, we are observing that this one we call that as eyepiece or eye lens, that is. Like this we have. Okay. Total two lens we are using. Now in the given question, in this simple microscope, which lens is used? But here actually our purpose is to see a magnified image, that is. If you are using a concave lens here, concave lens always forms a virtual, erect and diminished image only it is forming. But here in this case we need a magnified image. This magnified or enlarged images are formed only by the convex lens here. So that's why here if you want to use that in a microscope, we have to use a convex lens, that is, and two convex lens actually we use. And how that is useful is, whenever if you are taking the object here, Okay, if the object, if you are taking here, whenever the light is, if you are focusing that lens there, which is our objective lens, closer to the object, so that what happens there is, when compared to the focal length, the position of the object we have to focus like in between focus and optic center, that is between F and O, that is. Okay, then as the object is placed in between F and O, here what happens there is, this is the object, if you are taking that minute particle, if you are taking the object which is in between focus and optic center for our first lens here, then a magnified image it is forming here. Okay, according to the sixth special case we are having, it forms a virtual, erect and a magnified image is formed. In that way we can use, in case of this simple microscope, 2 convex lens we are using. Okay, total 2 convex lens we are using. Now, the next question given that a positive magnification greater than unity represents, means here mainly 2 things are there. One is that positive, another one greater than unity is given. Greater than unity, unity means 1, and the magnification which is forming here, it is greater than that unity is given. And a positive magnification is given there. So, which means we have to take that as more than plus. That m value is positive, m is positive and its value is more than 1 we are taking. For example, like this you can take, m is equal to plus 2, that is. Okay. Now, we know that positive or negative represents whether the image formed is an erect image or virtual image, that is. Following the rules for sign convention here, then whenever any of the object if you are taking which is above the principal axis is taken as positive, whereas below the principal axis actually we are taking that as negative, that is. When come to the case of magnification formula, we know that m is equal to minus v by u, that is. Okay, whereas m is equal to minus v by u, that is. Here that value given, m value is given as plus 2, that is. So, which means here we are taking plus 2, that is. And if you apply the sign convention here, okay, as the given one, it is about the positive there, magnification there, which is the case of the convex lens here. Okay, then in case of that one, then we are getting the image there which is v, and the object distance we are taking that which is always taken as a negative, that is, which is minus u, that is. Okay, then whereas as m is equal to minus of minus 2 here, then that image, that magnification we are getting plus 2, that is. Then that plus represents that is above the principal axis, which is formed for our special case here, where the image it is forming between, the object is placed between focus and optic center. The image is formed on the same side here, which is a virtual image is formed, that is. And whereas if you are taking that plus 2 represents when it is greater than 2 here, whenever m value is greater than 1, then it always represents about enlarged or magnified image, that is. Enlarged or magnified, that is. Enlarged or magnified. Now, m greater than 1, which is enlarged or magnified, and m value which is a positive given, which means that is of erect or virtual you can take, that is virtual and erect, and enlarged image is formed. Okay, that is its meaning here. Okay, so a positive magnification greater than unity always represents, it may be virtual and erect, or and it is given as it is more than 1 here, that is a magnified image is formed. So, finally, the property of the image characteristics become virtual, erect and magnified image. These type of images formed by only our convex lens, that is obviously the convex lens. Here it is given 2 questions are there. The power of a convex lens of focal length 50 centimeters is, given that it is a convex lens, that is. Convex lens at first it is having a positive focal length, that is, because it is forming a real image, that is. Okay. Thus the focal length here it is of a positive is there, f is positive we are taking. Then 1 by f value which is power is also positive. First we have to see this sign convention here. As focal length is positive, so that's why the power sign convention is also becoming positive, that is. Now, when come to the case of this focal length here, focal length it is already given, which is of 50 centimeters is given, and we need to find its power here. And we know that as power P is equal to 1 by F, where F means the focal length. This focal length actually we have to take that in meters, that is. Then we know that 50 centimeters is equal to 50 by 100 meters, that is. Okay, which is nothing but equal to 1 by 2 meters, that is half meter, that is. Okay, then as the focal length we got in meters according to our formula here, then the power of the lens becomes P is equal to 1 by F. Then 1 by F is equal to 1 by that focal length we got F is equal to 1 by 2 in meters, that is 1 by 2 meters. Then if you substitute that here, then you will get 1 by 1 by 2, which means 2 meter inverse we are getting. That meter inverse only we call that as diopter, that is. As the focal length is positive, as I said, here the power also becomes positive, that is. Then finally, the power of this convex lens is nothing but equal to plus 2D, where D represents that is a diopter, that is. Okay, so mainly we have to check total two things here. One is about the sign here, which is we got that as positive, and that positive represents it is about a convex lens, that is, which means the focal length is positive for that. And the next one is the magnitude here, which is 2D we got. While taking this focal length here, we have to take the focal length in the power formula in terms of units meters, that is. Okay, so that's why we converted that 50 centimeters into meters here, where 50 centimeters is equal to 1 by 2 meter, and if you substitute that, then we are getting P is equal to plus 2D, that is. Okay. Now, when come to the second case here, another question given here we have the focal length of the lens with power minus 1.5D is. So that power given there directly. So given is power P is equal to minus 1.5D. Now only I said that is about the sign convention here. So positive we are having if you have the focal length, then power is also positive, whereas if the power is it is of negative there, means the focal length is also negative, that is. So from this one it is clear that F is negative, that is. Focal length is negative in case of concave lens, that is. In case of concave lens, the focal length is negative. Now when come to the case of the magnitude here, which is 1.5 we have, and we know that power P is equal to 1 by F. Okay, here the power value is already given, so that's why from this we can write F is equal to 1 by P, that is F is equal to 1 by P. Then the focal length F it is equal to 1 by P value given, which is of minus 1.5 diopter, that is, where diopter is nothing but equal to meter inverse, that is reciprocal of the meter, that is. Then 1 by minus 1.5, take that minus here, minus 1.5, 1.5 we can write that as 15 by 10, and this is of 1 by meter, that is. Okay, that 1 by meter which comes to the numerator here, then focal length F is equal to that 10 by 15 meters, that is, and we are having a minus is present, minus. Okay, then we are getting here 5 3s and 5 2s, of which you will get minus 2 by 3 meters, that is. That is the focal length we got. Then if we calculate the value, then finally we got F is equal to minus 2 by 3, which is 0.66 meters we are getting. Okay, F is equal to minus 0.66 meters. Or if you want to convert that again into meters here, we can also write that as 0.66 into 100, which is of 66.66 centimeters it becomes. And if you observe here, again we are having a negative is there. So which means the focal length of the lens, that lens is nothing but given is a concave lens. And who is having a power of minus 1 by 5, 1.52 D means 1.5 D means the focal length is nothing but equal to 66.66 centimeters. Here given two more questions there. The first one is an object is placed 12 centimeters from a convex lens and whose focal length is 10 centimeters. Then image must be, means we have to consider about the characteristics of the image formed by this convex lens. Here mainly two things are there. The object is placed at 12 centimeters. So object distance is there, which is 12 centimeters, that is. And also given that the whose focal length is given as 10 centimeters, that is, which is f is given as 10 centimeters, that is. So we know u value and f value here. When you are taking in case of a convex lens here, then if you are taking a convex lens, which is, this is the optic center, and here you have the focus, and here we are having the center of curvature, which is twice the focal length given. Okay, here the focus or the focal length given, which is of 10 centimeters, that is, and twice the focal length, it becomes 20 centimeters, that is, 10 centimeters and 20 centimeters, that is. Now given the object is placed at 12 centimeters is given, which means the object we are keeping that at 12 means that is in between 10 and 20, that is. So the position of the object becomes in between f and c, or in between f and 2f. Then in this case we are getting, as the object is placed in between 2f and f, the image formation actually it is beyond 2f we have. Okay, beyond 2f we are getting the image there, like this. Okay, so in this case the image formed, the image must be means the image is formed beyond the center of curvature, and not only that, it is forming an enlarged image and inverted image that is forming. Okay, then here in this case, as the object it is of inverted is given there, as we are getting inverted there, then the magnification it will be minus, magnification value is minus. And not only that, here we are getting a enlarged image, so the magnification value it is of more than unity we have, means like this. As given, the focal length is 10 and object is placed in between f and 2f here, or f and center of curvature, the object, the image distance becomes, image is between 2f and infinite, which means beyond 2f, that is. And not only that, here it is forming a real image and inverted image is formed, and the magnification you see, that is an enlarged image is formed, which is the m value is more than 1, and not only that, m value is negative here. That negative represents that is of inverted image, that is. Okay, that represents that is an inverted image, that is. M is negative and m value is greater than 1 we have. Okay. Now if it come to the case of the next question here, when a person uses a convex lens as a magnifying glass, the object must be placed at a distance. So means at which place we have to keep the object, so that we have to use that convex lens as a magnifying lens, that is. Then as the object we want that as to be a magnified one we need. That's why in case of this, if you are taking the object in between f and c, or in between if you are taking between f and o, in both the cases we are getting an enlarged and a magnified images we are getting. But the problem with, if the object is placed between f and c, if you take between f and c, if you take, the image formed is inverted image, that is formed is a inverted image. Okay. So that's why here, as we need a object magnified image, that is, which is just like the object, that's why we have to take the position, the another position where we are getting a magnified image, which is in between f and o, that is, means when object is placed between the focus and optic center here, here we are getting a virtual, erect and magnified image is possible. Magnified image is possible here. So in this case, as the object is in between f and o, there we are getting a virtual image just like the object, which is again above the principal axis, and we are getting the erect image there, and we are getting a magnified image also. So these type of convex lens, actually these magnifying lens only we are using even in case of microscope also. Okay, in case of microscope we can use the same convex lens, and not only that, whenever if you want to magnify any of the object here, we prefer this convex lens. That to the object it is taken in between focus and optic center, that is, which is very much closer to the lens we prefer. Okay, so the answer becomes between f and o, and it is of virtual, erect and magnified image it is forming. Now here we have one more like numerical problem. An object is placed at 25 centimeters from a convex lens whose focal length is 10 centimeters given. Then the image distance is the question. Okay. So when you are taking these type of problems numericals, first we are having a ray diagram we have to think here. For example, as given it is a convex lens is there, this is a convex lens and object is placed in between, here object is placed at 25 centimeters is given there and also given that the focal length it is of 10 centimeters, that is. As the focal length is at 10 centimeters, then the center of curvature position becomes 20 centimeters, that is. F is at 10 and C becomes at 20 centimeters. But here if you observe, the object is placed beyond the center of curvature here, which means object is placed after the center of curvature position. For these type of position of objects, the image is formed in between C and F here. Then here it is forming the image somewhere in between F and C, that is. Means our answer, it should be in between 10 and 20 centimeters, that is. Okay, in between 10 and 20 centimeters. Now we will see exactly how much is that distance is. Okay. Now as given that as the focal length it is of 10 centimeters, that is, and object distance given which is of 25 centimeters and the lens we are using in case of convex lens, that is. First if you substitute the values in our formula, where our lens formula is 1 by F is equal to 1 by V minus 1 by U, that is. Then the focal length given it is of 10 centimeters, that is, and the image distance we don't know where we are taking that image there. Actually from the ray diagram it is clear that is it should be in between F and C, and minus 1 by object distance is given which is of 25 centimeters, that is. Then after substituting these values, at first we have to check the sign convention here. Then the sign convention, if you come, as it is case of the convex lens, so given is a converging lens which is a convex lens, that is. Then convex lens its focal length is a positive we have. So that's why F value 10 we have to take that as a positive, that is. So 1 by plus 10 is equal to 1 by V minus 1 by, in case of this object distance, that object distance we have to take opposite to the incident light ray here. So that's why we are getting that as a minus, that is. So that's why 1 by 25 with minus we have to take, because object distance it is of a negative, that is. Then 1 by V is equal to 1 by V minus of minus becomes plus by 1 by 25, that is equal to 1 by 10. Then 1 by 25 coming this side, it becomes 1 by 10 minus 1 by 25 is equal to 1 by V, that is, that image distance, that is. Then finally we get 1 by V is equal to, then if we take LCM to 10 and 25, then we are getting 50. Then 10 5s minus 10 2s, that is, which is 3 by 50, that is. Then finally we get 1 by V is equal to 3 by 50, or V is equal to 50 by 3. If you observe here that image distance we are getting which is of a positive value only we got. So means the sign convention here for the image distance formed by this convex lens is positive. So that's why the image is formed after the lens which is in the direction of incident light rays. We have to measure that distance here. As V is equal to 50 by 3, that is nothing but equal to 16.66 centimeters, that is. As the object is in between 16.66 centimeters, which is nothing but according to our ray diagram we got, that is in between focus and center of curvature, which is in between 10 and 20. So that's why our answer is correct. We satisfied both the image distance which is of a positive we got, and not only that, the image position it should be in between F and C, of which in between 10 and 20, of which we got the answer 16.66 centimeters. Like this, whenever any of the object problem if they give in the ray diagram there, depending on the numerical their given lens, at first we have to check our ray diagram first, where it is going to be the object position. After that take the lens formula, and after that substitute the values, and after that apply the sign convention, and finally check our answer it is correct or not by using the ray diagram. Now here we are having one more question on the power topic here, of which given that a spherical lens, we don't know which lens that is, has a focal length of minus 20 centimeters is given there, and its power in diopters we have to find there. So, as it is given, the focal length is there, which is minus 20 centimeters is there. So, focal length f given minus 20 centimeters. But remember, when you are taking the case of the focal length sign convention here, in case of the convex lens, we are having a positive sign convention we have. So, convex if you are using, we are getting f value, it is if positive. Then if you are taking a concave lens here, concave lens, the focal length values are negative we have. Okay, the focal length for convex is a positive, for concave that is a negative here. As the given question, as we are having minus is there, that minus represents the lens we are using. This spherical lens is nothing but a concave lens. That is our first conclusion we have. And after that, we are having that focal length is given as 20 centimeters, that is. So, for this concave lens, which is of having the focal length 20 centimeters, then we are finding the power in terms of diopters, that is. Whereas diopter, it is nothing but equal to the meter inverse, that is. So, as power is equal to 1 by focal length, where focal length in meters we have to take. Then as the focal length given, it is of centimeters is there, then f is equal to minus 20 centimeters, which is into 1 by 100 meters, that is. Okay. Then it becomes minus 1 by 5 meters, that is. That is the focal length in terms of meters, that is. Then if you substitute the value here in the power there, then power is equal to 1 by minus 1 by 5 meters, that is. Okay. Then that 5 come to the numerator, of which we are having minus is there, and we are having meter inverse is there. That meter inverse only we call that as diopter, that is. So, finally, we got the power of the given concave lens, because as we got here that minus, because of due to that minus sign convention is there for only for the case of concave. So, to this concave lens, it is having the focal length of 20 centimeters, is having a power which is equal to minus 5D. Of the given options, we are having minus 5D is there to the second one. Like this, if the question is given on power, mainly we have to remind two things about the sign convention, whether it is positive or negative, which relates to the convex lens or a concave lens, and another important one is about the units, so that all the focal length units we have to take that only in meters, that is. Now, given here, two thin lenses are there having the power plus 5D and minus 2D, that is. So, plus 5D is one of the power and another one is minus 2D, that is. Okay. So, here power P1 is plus 5D, which represents that is a convex lens, that is, and next one given which is of power P2 is equal to minus 2D, where that minus represents that is about a concave lens, that is. Okay. Now, these two power lens given there, and so that these two lenses are combined here. So that we have to find the final focal length of the combination here. We know that power is nothing but the reciprocal of the focal length, or focal length is nothing but the reciprocal of the power we have. At first, we have to find what is the combination of the power we are getting. As these two lenses powers are given there, directly we can find the total power of the combination becomes P is equal to P1 plus P2, that is. Of which, as it is of P1 plus P2, it becomes plus 5D and minus 2D, that is. Then it becomes finally plus 3D is the combination. Okay. Then the final power of the combination becomes plus 3D, that is. So, finally, as we got the power, now we can find for the case of focal length here. And we know that power is equal to nothing but the reciprocal of the focal length, that is. Or you can also write that as focal length is nothing but the reciprocal of the power. And this power, which is the combination of both the lengths we are taking, then that f is equal to 1 by power, where that power of the combination we got plus 3D, that is given as plus 3D. Whereas 3D, D represents that is of meters, that is. Then here as f is equal to 1 by 3 in meters we got. Okay, 0.33 meters. Then if you convert that into centimeters, that is then 0.33 into 100, that is. Then finally we get 33.33 centimeters, the final focal length. But if you observe here, the final focal length, which is the combination of both the lengths here, we are getting the power is positive. Power positive means finally that is acting like a convex lens, that is, which is a converging lens, that is. After the combination of using a convex lens and a concave lens having a minus to their power, this power combination we are getting a positive, which represents that convexo-concave lens. Finally, it is behaving like a converging lens. That's why here again we are getting the sign convention as a positive, and finally the focal length becomes 33.33 centimeters, that is, or 0.33 meters, which is a positive one we have. Here we have one more question there. The radii of curvature of a convex lens is 0.05 meters and another one is also 0.05 meters, and its refractive index is given 1.5 and its focal length we have to find here. As this is about a double convex lens is given there, a double convex lens. Now, in case of this double convex lens, the radius of curvature of the first one, which is 0.05 meters, and R2, that is also 0.05 meters, that is, or you can also write that as 5 centimeters, here this as 5 centimeters, that is, and its refractive index n value is given, n is equal to 1.5 is given there. Then what we need is we have to find the focal length here, and we know that the focal length formula, if two radius of curvature are given there for the given double convex lens, 1 by f is equal to n minus 1 of 1 by r1 minus 1 by r2, that is, n minus 1 of 1 by r1 minus 1 by r2. Then n value we already know that is of refractive index, which is 1.5. So 1.5 minus 1, and we are having 1 by r1 minus 1 by r2 is there. Then 1 by r1, that r1 value given, which is 1 by 5 minus 1 by 5 we have. Okay, and given lens, actually that is a double convex lens. We have to apply again the sign convention here. Then as r1 represents about the first surface here where the light ray strikes, that appears to be like a convex surface, that is. See here, this appears to be like a convex surface, that is. As it is of convex surface, the focal length of the first radius of curvature, it becomes positive, that is. And whereas whenever the light ray enters here, the other surface which is about R2, this side, we are having, it appears to be like a concave surface, that is. As it is of a concave surface, its focal length becomes negative, that is. So this is of minus we have. Okay. Then finally it becomes 1 by f is equal to 1.5 minus 1, which is 0.5 of 1 by 5 minus of minus becomes plus 1 by 5, that is. Then 1 by f is equal to 0.5, which is 1 by 2 you can write, and 1 by 5 plus 1 by 5, it becomes 2 by 5, that is. Then focal length finally it becomes f is equal to 5 centimeters, that is. Finally the focal length becomes 5 centimeters, and that if you observe the focal length value we are getting here positive, that is, because we are using a double convex lens here. So that's why as it is a double convex lens, here we are having the focal length also positive we are getting. And not only that, in this problem if you observe here, the focal length values we are taking the radius of curvature, which is of 5 centimeters, another radius of curvature is also 5 centimeters, and finally if you do the problem, the final focal length which is coming is also a combination of both, which is again a 5 centimeters, that is. So when you are using two equiconvex lens here to combine both, like a double convex lens, equiconvex lens having the same radius of curvature is there, then the focal length value also becomes, for the combination of both that one, it becomes again the same, which is of 5 centimeters, that is. Now given here, if the refractive index of water is 4 by 3 and glass is given 3 by 2, then find the refractive index of the glass with respect to the water, and also we have to find the speed of light in this medium, that is. So given that here refractive index of water is given there, that is nothing but its absolute refractive index, that is. Absolute refractive index of water 4 by 3 and the glass which is 3 by 2 is given there. Then we have to find the refractive index of glass with respect to the water. So, refractive index of glass with respect to the water, that is, which means here we are taking the light rays coming from water to the glass. So, whenever if we are having the refractive index of glass with respect to the water, means we are comparing the refractive index of the glass with respect to water here, which means nothing but refractive index of glass by refractive index of water, that is. Okay. Now, as the light ray is coming from glass to water here, now glass it is of given refractive index 3/2, whereas in case of water it is given 4/3, then it becomes 3/2 of 4/3 means in reciprocal you will get 3/4, that is, which is equal to 9/8, that is. This is the refractive index when you are taking glass compared to the water here. But also here it is given that we have to find the speed of light in this medium when the light ray is going from glass to the water here. Then as it is going from glass to the water here, so that the final refractive index, the relative refractive index we are getting 9/8, that is. Okay. As it is given that a refractive index of the glass it is equal to 9/8, then how much is the speed of light increasing? Now we are finding that. Okay. As it is given that refractive index in case of water, that is of 4/3 is given, as it is of 4/3 is there, then n is equal to, we know that is of c/v, that is. As n it is equal to c/v, where n is the refractive index of the first case we are taking, as it is started from water, we are taking water here, then it is equal to c is 3 into 10⁻⁸ meter per second by its velocity given there. In case of water we are finding of each velocity of that in water we are finding. Then as it is of velocity in water if we are finding, and we know that refractive index of water is 1 point, that is of 4/3 is given, then 4/3 is equal to 3 into 10⁻⁸ by VW, that is. Okay. Then the velocity of the water is equal to, which is 3 into 10⁻⁸, and if you cross multiply that into 3/4 you will get, of which velocity of the water becomes 9/4 into 10⁻⁸ meter per second it becomes. Okay. Whereas that velocity of the water is nothing but equal to 2 point, of which 4 2's get cancelled there, 2.25, that is, into 10⁻⁸ meter per second. This is the velocity in water you are getting, which is 2.25 into 10⁻⁸ meter per second. Whereas if you are taking in case of this glass, if you are taking, then in the same way if you find for the case of glass, okay, in case of glass if you are taking, then Ng is equal to, again, c/v if you are taking, where velocity of the glass we are finding, velocity of light in the glass we are finding, then velocity of the light in the glass is equal to, c is 3 into 10⁻⁸ meter per second by its refractive index, it is given that as 3/2, that is, which is of 3/2 meter per second, that is. That 3 get cancelled and we are getting Vg is equal to 2 into 10⁻⁸ meter per second. So, this is the case we are getting velocity in glass, which is 2 into 10⁻⁸ meter per second, and velocity in water it is of 2.25 into 10⁻⁸ meter per second. So, when compared, if you observe that the velocity of light in that water is more, which is of 2.25 into 10⁻⁸ meter per second is there, whereas when enter into the glass here, as it is coming from water to the glass, then if you compare the velocity here, then it is becoming 2 into 10⁻⁸ meter per second it becomes. So that there is a decrease in the speed of light takes place once it enter into the glass, because that is acting like a denser medium, that is. So that's why here if you observe the refractive index value we are getting more than 1 if you are comparing the glass with respect to the water, that is. Now given question next one is, an object at bottom of a beaker filled with a liquid up to 10 centimeters height here. If the refractive index of the liquid with respect to the air, because the light ray is coming from air into this liquid here, is given as 4/3, and we have to find the apparent depth of the object here. We know that one of the important effects of the refraction, when you are taking any of the object inside some transparent liquid like water you take, there is a change in the position of the object here because of due to refraction effect, that is. Here given that the object is placed in a beaker, that beaker is filled with a liquid here. That liquid height it is given, which is of 10 centimeters is given there. Okay. Now, as it is raised to a liquid height here, which is of 10 centimeters, and the refractive index n is given as 4/3, the coin, the object which is placed at the bottom, let us suppose this is the object. Now, that object appears to be raised here. Then actually this 10 centimeters is the original depth here, whereas because of due to refraction, there is a change in the position of the object we have. This we call that as apparent depth. This is called as apparent depth. Let it be that is x. And this 10 centimeters is nothing but called as real depth, that is. And this is apparent depth and this is the real depth. And this is the height of which that coin appears to be raised. There is a change in the vertical position of the coin here. Now we are finding that x value, that is. Then we know that according to that refractive index n is equal to, which is given, that is of glass water with respect to the air there, or the liquid with respect to the air there, given that is of 4/3 is there. Then we know that according to that formula, which is of real depth by apparent depth here, where the refractive index is real depth by apparent depth, that is equal to 4/3, that is. Then the real depth actually it is given that as 10 centimeters, that is, and apparent depth which is we are taking that as x is equal to 4/3, that is. Then if you cross multiply that, then you will get 4x is equal to 3 into 10, 30 centimeters, that is. Then x is equal to 30/4 centimeters, that is. Okay, of which we are getting that is equal to 7.5 centimeters, that is. So which means actually the original depth of the coin, it is of 10 centimeters is placed at the bottom of the beaker. But here it appears to be that x value which appears to be raised, that is of only 7.5 centimeters is present. So means our x, which is that object appears to be raised by 7.5 centimeters, that is. And we are having, there is an increase in the, there is a change in the position of the coin is coming, which is that is coming up here. So that this, how much is the vertical shift we have? Shift in the position or displacement shift, it is equal to 10 minus 7.5, that is, which is equal to 2.5 centimeters, that is. Okay, 10 minus 7.5, which is 2.5 centimeters we have. So like this, when an object is placed, when you are taking inside any of the liquid, always there is a change in the position of the object we have because of due to the refraction effect. In this case, when you are taking a original depth of 10 centimeters is there inside that object which is placed at the bottom of the beaker here, it appears to be raised by 2.5 centimeters, so that instead of showing that as a 10 centimeters object depth here, it is showing the depth as only 7.5 centimeters. This effect only we call that as apparent depth effect in case of refraction, that is.